We are Meta Mobility Lab at Carnegie Mellon University, and this video is about our latest study, optimizing locomotor task set in biological joint moment estimation for hip exoskeleton applications. Recent approaches in exoskeleton control utilize the estimation of a user's biological joint moment and apply a reshaped scale version as the assistant profile. Estimation using a deep learning model with wearable sensing has demonstrated significant performance benefit across a wide range of activities. However, by the nature of deep learning, it requires large datasets that comprehensively represent various activity modes. Therefore, the costs and resources for data collection and model training are substantial. Here we question, is it possible to make a task-agnostic model with less data collection? Some studies have explored this by using 4-task selection algorithm. They discovered that training with just 8 to 10 out of total tasks can achieve optimal model performance. This suggests that not all tasks are necessary for effective model training. However, it's unclear why certain tasks are more beneficial than others. Current methods rely solely on model performance for task selection, lacking biomechanical explanation for these choices. In this study, we propose optimizing locomotor task selection through cluster analysis in a reduced biomechanical feature space. We use segmented and averaged hip joint moment, velocity, and angle profile for each subject task combination. By principal component analysis, we reduce the dimension of these features and perform k-means clustering of tasks in this feature space to identify the most representative locomotor tasks for training a hip joint moment estimator. These are the variances explained by each principal component and the silhouette score assessment for K clusters. Based on this result, we created a 3-dimensional biomechanical feature space and 8 clusters of different task data points. Since each cluster contained a different task, we developed a task weight analysis formula to calculate R, the representativeness of a task for a cluster. Using this, we accounted for the data proportion, subject diversity, and the difficulty associated with data collection in our task selection process. The table shows the task weight analysis result for each cluster. From a total of 20 tasks, our approach reduced it to only 8 tasks. Furthermore, it clearly demonstrates the clustering of similar locomotor tasks, such as cluster 2 for non-cyclic propulsive movements and cluster 3 for cyclic and ascending movements. We trained an FCNM model with this optimized task set and compared the result with 2 other conditions, or tasks using the entire dataset and cyclic tasks using only cyclic locomotor task data. These are the final averaged RMSE and R-square values for models under each condition. The optimized task set model achieved comparable performance to the all-task model. This result validates the effectiveness of our task set optimization. Additionally, the optimized task model outperformed the cyclic task model, highlighting the importance of non-cyclic tasks in the training data. These comparisons show the ground truth and estimated hip joint moment values from the all-task and optimized model for 2 cyclic and 2 non-cyclic movements. The optimized model produced predictions nearly identical to those of the all-task model. When the predictions were poorly made, the all-task model also underperformed. This suggests that these difficulties are not stemming from the training task set, but from the limitations of using simple FCNM model and the inherent challenges of predicting non-cyclic tasks using only kinematic data. Overall, our study provides a systematic locomotor task set optimization method grounded in biomechanical features, offering not only cost-efficient but also more interpretable task selection for model training.